So question 6 gives us a rod, rough horizontal ground and a smooth wall. Rod's making an angle theta with the ground, it's resting in limited equilibrium, and it's a uniform rod. And there are facts about the mass and the length of the rod which I will add to the diagram, and then we'll go on from there. Okay, I think I've added most things to the diagram. The important things is because it's a uniform rod, I'm able to put the centre of gravity right in the middle, so this distance, which splits the rod in two, is A and A respectively. There is an angle theta in here, which will come into play when we resolve this force. There's only a reaction force from the wall because the wall is smooth, but because the ground, the horizontal ground, is rough, the rod will attempt to slip down, so the motion of this bottom part of the rod will be to come in this direction. So the friction is acting backwards. So in a way, that's answered part A. You could write that out in a few more words, but the rod's going to slip down the wall, which means that the friction will oppose that motion by trying to hold the base of the rod at A here. I've just noticed that I've got to call the normal reaction force on the wall as S. So using the fact that the rod is uniform, we can answer B, C and D. Okay, B. By taking moments about A, show that this equation is true. Okay, so let's do what they say. We're going to take moments around A. So because we're taking moments around this point, both RA and F don't come into our equation. What forces are left are the force due to gravity, here mg, and S, which we will both have to resolve so that they act perpendicular to the rod. So resolve. Have to choose a direction. Let's choose clockwise as the direction. So I'm choosing clockwise as the direction to resolve about A. So going in that positive direction, I have mg, but I have to turn it through theta. There is another theta in here. Crank that force around so that it's perpendicular. I get mg cos theta. And this force acts at a distance of A away from A. So this is multiplied by A. This force is trying to oppose this motion, so we have to take it away because it's against our rotational angle. So it's negative. The force is called S. Now there is another theta in here. So when I resolve this force so that it's perpendicular to the rod, I'm moving it through 90 minus theta. And if you do that, the reduction of S will be S sine theta. And this force acts at a distance of 2A away from the resolving point A, and this whole thing must be equal to 0. Straight away, the A's cancel. Making S the subject, I get that S is equal to mg cos theta over 2 sine theta, which is what they've set up here. So this is a half mg cot theta. And that's the first of the answers. We've now been given a value for the coefficient of friction mu, and it's in terms of theta, and we're given that tan theta is equal to 3/4, at which point I always draw a little triangle opposite 3 here. This is 4, this must be 5, and this is theta. It means I can very quickly calculate cos theta and sine theta from this 3, 4, 5 right angle triangle. Now, because we're told that we're in limiting equilibrium, the friction force here is related to the reaction force at A by mu. And I can say that F is equal to mu RA. Now, if we resolve horizontally, the only horizontal forces are F and S, so these must be equal. Equally, if I resolve vertically, the only two forces available are RA and mg. These two, because we're in limiting equilibrium, or in equilibrium anyway, these two must be equal. So if I put all of this into our equation here, S we know and RA we know. So therefore I can say that mu mg, which is another version for mu RA, is equal to S, which is this lot here, which is a half. mg cot theta. Happily for us, the mg's cancel each other out, and I'm left with that mu is equal to a half cot theta. Cot theta is the upside down version of tan theta, so this is equal to a half multiplied by 4/3, which makes mu 2/3. And that's the answer to part C. And part D asks us for the resultant force at A of both the reaction force and F. And we need to do this in terms of M and G. So the force going upwards, so we know that RA is equal to mg, and as F is equal to mu RA, F is equal to 2/3 mg. So we've got two forces, one acting vertically, one acting horizontally. We need to form a force triangle. And the force at the top is 2/3 mg, and the force here is mg. So we need to do a Pythagorean calculation to find out what this force x is. So x will turn out to be mg squared plus 2/3 of mg, also all squared. And if you work that out, this turns out to be the square root of 13/9 mg, which if you simplify the root 9 becomes root 13/3g. And that will be your answer. Okay, now to part E. We're told that the rod is now not uniform and the centre of mass has moved closer to B up this way, therefore. And with this value of tan theta being equal to 3/4, the rod hasn't changed its attitude between wall and floor. State whether S, the reaction force here from the wall, is larger, smaller, or equal to the S when the rod was uniform. So here's the new situation. I've moved mg from its original centre position nearer to B, as the question has indicated. Now, all we've got to do to solve the problem of whether S is larger or smaller or the same or whatever is consider moments around A again. The force of mg is the same. The rod hasn't changed its mass. It's just changed the position of the mass because it is now non-uniform. So mg itself will exert a greater turning force in the clockwise direction. So if this rod is to remain at rest against the wall and the floor, S will have to be larger because when we turn it to be perpendicular to the rod, the value of S will have to be larger because its distance from the point A, because we're taking moments, hasn't changed. So S itself will have to go up. So all you've got to do is write that in a sentence to gain the 1 mark available in this question. And here's my answer. As mg is now further away from A, its turning effect clockwise will be greater. Therefore, if the rod is to remain in equilibrium, S will have to be larger to compensate. And that will gain you the 1 mark available here.